What is going on, chemistry fans? It's your boy, Cadet Sergeant Ryan Kreiser, back at it with another banger physical chemistry video. Now, before I get any further, please remember to smash like and subscribe and ring that notification bell. Now, today we're going to be talking about something a little bit different, and unfortunately, it's not about methanol. But don't worry, I've got plenty of carbons and hydrogens and oxygens, just like I would with methanol. We're going to be taking chemistry into the future using computational chemistry. So for this lab, we're going to be using computational chemistry to determine the exact molecular geometry of a bunch of small molecules. Now you may be thinking, Cadet Sergeant Kreiser, I've already learned molecular geometry in Chem 1. It was super easy. There's these four shapes. You got tetrahedral, you got your trigonal pyramidal, you got your trigonal planar, and you got your linear, right? Right? Wrong. They're all wrong, you understand me? It's so much more complicated than that, except for linear. Linear's cool. Linear can stay. To show you what I mean, here's a simple illustration. Here we have an oxygen bonded to a carbon and a hydrogen, and that carbon is further bonded to another hydrogen. This isn't a real molecule, it's just for illustration, although I suppose it could exist. So, from general chemistry, we know that this molecule has a bent geometry, especially around this oxygen, because we've got two lone pairs and we've got two bonding domains. But what we don't know is, what are the exact bond lengths? Are there any dipole moments between the two? What's the exact angle of that oxygen-carbon-hydrogen bond there? And furthermore, what impact do the lone pairs of oxygen and its electronegativity have on the dipole moment between carbon and hydrogen and the bond angle between hydrogen, carbon, and oxygen on the left-hand side here? These are all things that are very thermodynamically relevant, especially as we start to talk about molecules in solution. Today, we're going to use a computational program provided by the University of Alaska-Fairbanks to determine the Gibbs energy of solvation for four small molecules. Alright, so here we are at our WebMO program from the UAF. To get to this page, you can just take this URL, put it in your browser, and then enter the username guest and the password WebMO. WebMO is nice because it's good enough to handle small molecules fairly quickly, and there are relatively few people on it at any given time. So what we're going to do here is we're going to create a new job, and we're going to build a molecule. Today let's build ethene. So you go here, you can select your atom that you want to build with. You can select more from the periodic table if you need. And then here you can see, did not mean to do that. You can create multiple bonds. You could even create ethyne if you wanted. I don't think I'd like to today. And then you can use this broom and this wrench in order to make structures that make sense. Now, what we're going to do is we're going to use the selector tool here to find out some things about this molecule. So here's WebMO's best guess without doing any real math for what the bond length is going to be between these two molecules and what the bond angle is going to be. Now, pay attention to these variables because we're going to check and see how correct WebMO actually is moving forward. We're going to take this job, we're going to use the Gaussian potential, we're going to calculate geometry, optimization, and vibrational frequency using this theory and this routine, and we're just going to hit this arrow. Now we're going to wait a couple seconds. Here, as you can see, this is complete now. You can click on this and it'll take you here. You go to the selector tool again, and you can see we have a slightly changed bond length here and a slightly changed bond angle. So this may seem like a pretty small change, but it's going to be more and more relevant the more we care about the behavior on the margins. A good example of this is Gibbs energy of solvation. Gibbs energy of solvation is usually pretty small compared to Gibbs energy of formation, the enthalpy, the entropy, these other thermodynamic qualities. So it can be changed significantly in the solubility of something in a solvent can be changed significantly by a small change in molecular geometry. So now that we've got our optimized geometry, we're going to try and use that to calculate the Gibbs energy of solvation for this molecule. So what we're going to do is we're going to go to New Job using this geometry. We're just going to hit this arrow, and we're going to proceed with this. But instead of optimizing close vibrational frequency, we're going to go to molecular energy. Now don't hit this arrow just yet. We're going to go to advanced settings and set the solvent to water. Then we're going to change a couple things in this preview window. This preview window shows what will happen if you use these exact settings. However, we're going to change some of these a little bit. So this is only going to give us the behavior in water. It's not necessarily going to give us the behavior compared to what would happen if it were out of water. What we're going to do is I'm going to copy and paste this line in. Now, Dr. Washington supplied this line, and I'll be honest, I don't exactly understand how these procedures work, how the coding language that WebMO uses works, but you can do a lot with these advanced settings, and I'm sure there's some documentation somewhere you can look at, or you can simply use this exact line to get these exact results that I'm running right here. And now, click Submit Job. It's going to give you this warning. We know that this code is appropriate, so we're going to hit Continue. So here we are, we're waiting a little bit. It's going to take a couple seconds for this to be completed. And look at that, 9.2 seconds. That's pretty fast. So now we're going to go here and get our raw output. We can get our Gibbs energy of solvation by scrolling down here to the bottom. And delta G of solvation is 1.43 kilocalories per mole. So you can see that's pretty high. It is positive, which shows that ethyne does not want to be soluble in water. Now this tracks with our understanding of ethyne as a nonpolar molecule. So you would expect these results to make sense. But now we've got an exact value for that. We can use that to determine our activity coefficient and understand a lot more about the behavior of ethyne without ever having to set foot in the laboratory. Alright, so here let's talk about some of my results that I ran. So I used a couple of different molecules, which are shown here. I used carbon monoxide, I used cyclobutane, I used dimethyl ether, and I used water. Here's a depiction of their molecular symmetries. You can see that this gives us a lot of ease for understanding the bond lengths and the bond angles, because across all these lines of symmetry, things are the same. So these angles are the same as these angles, and these angles are the same as these angles. Same thing with the bond lengths. You can see here that cyclobutane's got 5 axes of symmetry, which is very convenient for us. So using the WebMO tools, I was able to calculate these dipole moments, these bond angles, and these bond lengths. I moved on to these 4 molecules, ethane, phenylidene fluoride, ozone, and 1,1,1-trifluoroethane, to determine delta G of solvation. Now this is really interesting. The only one of these that is negative is ozone, which indicates that ozone should be very soluble in water. This is actually something that the literature conflicts on. Some people say that ozone is not soluble in water at all. Some people say that ozone is very soluble in water. Now you can look that up in PubChem if you're interested. It's got some conflicting sources. But here we can see that, at least theoretically, ozone ought to be very soluble in water. So what's the point of all of this? Why are we doing all these computations? Well, to start with, it saves us a lot of time. A lot of the molecules I looked at are gases at room temperature, and they're gases pretty far below room temperature. So it's hard to get them in a form that you can work with and dissolve them in water in a way that's reproducible experimentally. Doing computations like this can give us the information we need without having to actually look at how they behave in a physical building. Furthermore, it gives us an understanding of how even a small difference in the structure of a molecule can have serious implications for how it behaves on the margins. So, something I noticed for dimethyl ether, which is one of the molecules I studied, is that there was a 4-degree difference between the bond angle between oxygen, carbon, and hydrogen for the hydrogens that were directly across from the oxygen and its lone pairs, and the hydrogens that were shunted off to the bottom. This is something that I never would have known without doing some computational chemistry. Well, that about does it for today. Thanks for sticking with me to the end. Please remember to smash like and subscribe. If this video hits 50,000 likes in the next week, I will send a tinfoil hat to the first 10,000 people who liked it, so that you can become your own lightning rod, stand in the middle of the field, and create your own ozone right around you. Hope this video has been of some help to you, and I hope you have a great rest of your day, understanding more things about thermodynamics. Molasses. Take care now.